Yes, dear audience, my name is Claudia Link. I'm the head of the department Optical Systems here at Vision and Control GmbH. And I want to present the latest developments in the field of telecentric large field lenses and telecentric line lenses from our company. So here's the outline of my talk. I will start with an introduction of our company. Then I will present some basics to our large field lenses and to the theoretical values of resolution and depth of field of these large field lenses. Then I will present two new series of telecentric large field lenses and two products for telecentric line lenses. And I will close with a summary and an outlook. So who are we? Vision and Control is a global active OEM supplier of photonics-based components and solutions. And we have a broad know-how in the field of optics, for example, digital imaging and optical metrology. And we have a large catalog portfolio, and this is the showcase for our technology and quality. And we want to support leading machine and system manufacturers in the field, for example, of semiconductors, life science, or industrial automation, to achieve their aims. And we are now more than 32 years on the market. We are located in Suhl, in Thuringia, in Germany. And we have in-house research and development departments for optics, lightings, and vision systems. And we also have an in-house production and testing opportunities in our company. So we have a coordinated modular system of optics, lighting, and multi-vision camera systems. So we have a standard catalog, and we are also an OEM partner. So what are the basics for the telecentric large field lenses? What is the background? The challenge for telecentric lenses is always the diameter of the object we want to image, because the front lens must be at last the dimension of the test object or the imaging object. And if this diameter exceeds 200 millimeters, then I have to close it. Okay. Then cost, weight, and mounting effort increases dramatically for lenses made of glass. And this leads to a limited industrial usability of telecentric lenses. And we have here the Fresnel lens approach, which enables lightweight designs, but also cost-reduced and of course also less mounting effort, reduced designs. And the biggest large field lens which we have implemented was a customized service for a free aperture of 590 and times 580 square millimeters. So what is what is a okay. So what is the working principle of a Fresnel lens? We have a normal lens of which where big advantage can also be aspheric with higher aspheric coefficients. And the surface of this lens is projected onto a flat surface. It is also called a stepped lens. So it builds very flat, and it is very light because it is mostly made from a plastic material, for example, from PMMA. And what are the achievable resolution and depth of field of these large field lenses? So I have here the definition of the resolution. We use usually the modulation transfer function. I have here plotted the diffraction limited curves. They can be calculated. And if we look to this formula, we can also calculate the maximum spatial frequency, which is correlated to the wavelength and the numerical aperture, or inverse to the F number, which is here assigned by N. And the structural detail in the image side is then the reverse value of this maximum spatial frequency. And here the curves are shown for a typical F number 8 in machine vision and for different wavelengths. And we see that we have higher spatial frequencies for blue than for red or infrared. So, and because we want still have a contrast in machine vision, we say the maximum resolution is there where the contrast decreases to 20%. This is this line, and then I can get the maximum spatial frequency. And this I have listed for our two new series of telecentric large field lenses for two typical F numbers and two typical colors. We have here, for example, the maximum spatial frequency for blue for the F number 8 with 180 line curves per millimeter. This corresponds to a structural detail of 5.5 microns in the image side. Or, for example, the F number 16, we have the double structural detail, which only can be resolved with 11 microns. And now I want to come to the object side, to the resolution. I have to take the magnification of the system into account. And here I have the magnification of 0.04 for the new series TL380. And then we see we have, for example, at F number 8 and in the blue, we get a structural detail in the order of magnitude of 140 micrometers at F8, and at F16, for example, in the order of magnitude of 275. And it is, the structural detail resolution is higher if the magnification is also increases. And yes, we see the typical values which we can expect for the large field lenses with these magnifications. So what depth of field can we expect from this telecentric lenses? Depth of field, and we have to look to the depth of focus, which is image-sided, and depth of focus and depth of field are optically conjugated. We have here the special case for telecentric lenses that the depth of field in the object side is symmetrically, and we can have an estimation by a formula, and I found out that the wave optical part of the depth of focus fits very good for estimating the depth of field of the telecentric large field lenses. It is defined when the defocus when I image on a pixel and then it is decreased the maximum intensity by 20%. That means it is 80% is intensity if I go away from the ideal image position. And then this formula can be given. It is deduced in the literature, and we see it is dependent on the numerical aperture or the F number and the wavelength. And now I want to come to the object space again, and here I have to take the magnification squared into account. And here we have the correlation that the depth of field is the depth of focus divided by the depth magnification. And we have the following formula. And again, I have a table where I can see the values which can be hold for our telecentric large field lenses. For the first one with a magnification of 0.0 and a wavelength of 470 nanometers. We have, for example, for F number 16, a depth of field of 300 millimeters, and for the larger magnification of 0.06, we have a depth of field of 104 millimeters. So now I want to present the new series. First, the TL230 series. This is a series of 3 telecentric large field lenses for 3 different colors. The maximum object field diagonal is in the name of the lens. It is 230 millimeters. The maximum sensor is a 1-inch sensor, and the maximum image field diagonal is a little bit less than the sensor diagonal. It is 15.6 millimeter. Working distance is 320 millimeters. It can be adjusted by an adjustment of the basic lens, so it can also be reduced. It has a standard C-mount thread. And here you see the weight is 4,280 grams, which is not much for this dimension of a lens. And here I have a comparison to a telecentric lens that is available on the market for this order of magnitude of front diameter. It is here 220 millimeters. And here you see the comparison of the lens length. And you see also that we have weight reduction with our Fresnel approach. So here I want to present some measuring results. For imaging, I have used a spot which is also in our portfolio, which I directed onto a diffuser disc. And though I have a large illumination field, here you can see a metallic catalytic converter. It is imaged by the telecentric lens, and I have used this camera with this sensor size as a pixel pitch of 3.45 microns. And here you see an image of this catalytic converter. We can see through the holes of this converter, and we can prove if there is dirt in the holes which clogs them. And the image was taken with a wavelength of 417 nanometers and at f16. Here I have a finer structure of a catalytic converter. You can also see very good if dirt clogs the holes. And for illumination, we have another principle tested because we use the Fresnel lens also for illumination, our test object. This is a reverse principle of the telecentric lens, and the advantage of this principle is that we have a better edge with visualization, and you can use it if the detail resolution is not important. And one big advantage is also that the exposure time is very strong reduced. We had to use a gray filter in our telecentric lens that we can do the imaging. And here we see the measuring setup. We have here the telecentric illumination, TZB 230. Here's a metallic catalytic converter, and here the telecentric lens with the same camera. And here I have illumination and the image with the telecentric illumination. And I used, as I said, a neutral density filter with 1,000 times. And we see here that the illumination is telecentric because the little glass bottle is black, and only a small light bar is can pass through the glass. Now I want to present a second telecentric large field lens. This is a TL380 series with a maximum object field diagonal of 380 millimeters. The maximum image field diagonal is 15.2 millimeters, and the working distance is 400 millimeters. It also can be adjusted, the basic lens of this telecentric large field lens. It has also a C-mount connection. And here you see the lens length and the weight, and it is still under the weight of the competitive lens from the market, which was made all of glass lens. It has 9,000 gram, and this has a magnification 0.04. Here I have the measuring setup. I again used the the spot of our portfolio with this name, and I directed it onto a diffuser like this, so I can get a very large spot for elimination. And here I have imaged 1941 target that I can make some appreciations of the resolution. Here's the image of this target, and I have measured a resolution of a detail resolution of nearly 200 micrometers, and the theory predicted 137 microns, and you see that it's nearly on the theory. Even we have a Fresnel lens as a front lens. So here I want to show the test of the depth of field. I imaged a ruler. Here it is 0 degree. This means perpendicular to the optical axis of the setup. And here you see the image width is 360 millimeters. And here I have the ruler turned to 35 degrees. And from this arrangement, I could calculate that the depth of field, because all it is sharply imaged, is 300 millimeters. And you see we can predict it very good by the theory I have given you in this presentation. And here I have imaged a profile from aluminum with the width of 300 millimeters, and we can see the telecentric is very good, and it is also the edges are also sharply imaged by the large field lens. So, and the next part I want to present the telecentric line lenses. Here we have an image of the telecentric line lens TLL 400-28. And it has also a Fresnel front lens, which is cutted to a small section. And we have here also the width of the object field is 400 millimeters, as it is signed here. We have a magnification of 0.07, and here you can see the dimensions of this telecentric large field line lens. We have a width of 440 millimeters and a height of 85 millimeters, and the length is 630 millimeters squared cubed. And another product we will bring in our catalog is a TLL 420 to 28 millimeters. I didn't mention it. It's calculated for a 28 millimeter line with an M42 mount, or as the presentation before, M42 times 1 mount. And we have a larger width of the field, which is given here in these parameters. Yes, then now I want to give measuring results. Here you see the prototype of the TLL 400. Here we have an aluminum profile, the same as in the measuring setup before. I have also used the spot directed to the diffuser disc to eliminate this profile. And here we have a first image where you can see that it is a small bar with a full profile width that can be imaged. So then I come to summary and outlook of my talk. I have given you the basics of achievable resolution and depth of field for telecentric large field lenses. I have presented 2 new series of telecentric large field lenses, the TL230 and the TL380 series. They come in standard for colors blue, red, and near infrared. And the telecentric, I have presented the 2 telecentric line lens series for an 28 millimeter line. And we have here 2 standard products in our catalog for the blue wavelengths. And in an outlook, we plan to customize this products that you can fit it to your sensor size and to your object field size. And also we offer customized development of our standard telecentric lens portfolio. So I come to the end of my talk. I thank you for your attention and I'm open for questions.